class recording has started. So, yesterday we started talking a little bit more detail about gravity. And we introduced gravity earlier on in the unit, as one of the fundamental forces that exist out there in the real world, in the universe. Okay? But then we spent a little bit more time talking about gravity in detail, and we said that we can find the force of gravity on something, where is it? Okay, right there it is, by taking its mass and multiplying it by the acceleration that gravity causes at whatever location we're at. So in the case of Earth, that acceleration is around 10 meters per second squared. So we can figure out the force that gravity is acting on an object by taking its mass and multiplying it by 10. And that'll get you the force that gravity is acting on that object in newtons, which is different than the weight or the mass, right? And I think we talked about this, right? That this had sort of short answer question written all over it. So at least go ahead.
For the second one,
Yep.
Is it because it's the same because mass doesn't change regardless of location?
Mass doesn't change regardless of location, or you could say that, at least you could say something to the effect of that mass measures the amount of stuff that an object has, and that doesn't change regardless of where you move it to.
Do you know if this is Savannah's?
It has your name on it. This year's.
Yeah. Okay, I missed some. He wants me to get it too. Because I'm honest.
Now you won't be cold. All right, so at least you can think about it in terms of just in general that mass doesn't change based on location, but also because mass tells you how much matter is there, and that's not going to change when you move it from this place to that place. Okay. All right. At the end of class yesterday, we watched this stellarly produced video. Okay? And I'll play it again for you. I'm not going to make you listen to the narration again, but, okay, so we talked about that when we see objects falling here on Earth, that, we drop that feather and that penny, and the penny falls very quickly to the bottom of whatever it is we're dropping it, and the feather sort of nonchalantly takes its time as we fall to the bottom. Okay? But if we can change the conditions where we can get rid of air resistance and focus just on the effect of gravity, we would find that when this penny and this feather get dropped, that those two objects will experience the same acceleration. So they drop and they end up hitting the ground at exactly the same time. They speed up faster, 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 and this awesome instant replay here is going to show us that as it falls, right, you see them there right next to each other, both picking up speed, both going faster, until eventually they hit the bottom at the same time. Maddie, go ahead.
Does that mean if you took away gravity, everything would fall the same?
No, it wouldn't even.
Gravity's not the problem. Okay? Gravity's not the problem, it's the air resistance that's the problem. Okay? So we're gonna talk about that a little bit more today. Alright? So, at the end of class, I showed you this video, and did I do the demonstration for you where I dropped the object when he dropped the object?
Yeah.
Okay? I'll do it again here, just, So here we have astronaut David Scott, who is Apollo 15 on the moon. And he has a hammer in one hand and a feather in the other hand. And just for fun, because this is what astronauts do, they test the laws of physics. So he takes these two objects and he drops them, but I'm going to drop it too. And we see that his hammer and his feather both hit the ground at the same time. But my object hits the ground before their objects do. Okay? Good there? All right, so let's start analyzing this a little bit more, and let's talk about these two pictures that show up on the front side of your outline. Okay? So first, when we drop the object here on Earth, and when we drop an object on the moon, we find, and I just showed this to you, that the rock falls faster on Earth than it does on the moon. Why? Why does that rock fall faster here on Earth than it does on the moon? Katie?
There's no air resistance.
Something different than that.
There's gravity. It's stronger on Earth.
Okay. Gravity here on Earth, right? The Earth has more mass, therefore the force of gravity is bigger. If the force of gravity is bigger, more acceleration. In that case, it speeds up faster. So that accounts for the difference in an object falling on the moon versus an object falling here on Earth. That we see the object here on Earth will hit the ground before that object dropped on the moon. Okay? Good with that. Now, let's talk. Do we have enough time to summarize that? So let's talk about this picture. Here we have two objects, a feather and a rock, or in the case of the video, a feather and a hammer. And when we drop them, they end up hitting the ground at the same time. If we focus solely on gravity and the effect of gravity, all right? These objects, and we saw in the video, and we saw in the two pictures in the video, will have the same acceleration. But earlier in this unit, we learned that two things affect acceleration, right? Maddie, what are the two things that affect acceleration?
Net force and mass.
Net force and mass. And just to review quickly, because I did this in the last class, just to make sure we got this stuff down, got this picture. Okay? So, if we have two objects that are the same mass, let's say these are two bowling balls, okay? And I push one on them hard and push on one of them hard and one on them lightly, which one would experience the greater acceleration, red or blue? Red, right? Because increased force causes increased acceleration. We see that relationship here because what do we know about these two objects? If they're the same bowling ball, that means they have the same mass. Okay? So this relationship exists, direct relationship between force and acceleration, if these two objects have the same mass. Okay? If I take a bowling ball and a golf ball and apply the same force, we see that the bowling ball has a much smaller acceleration than the golf ball. Because what kind of relationship exists between mass and acceleration? The inverse relationship. And we'll see that as long as we apply the same force. Good so far? Okay. But gravity doesn't quite fit into these two situations, these two scenarios. Because as we look at this object, right, do they experience the same force of gravity? Do they experience the same force of gravity? No. Because remember, we said that the force of gravity can be figured out by doing m times g, right? Does the feather have the same mass as the rock? No. So which one experiences more force? The rock. That's true. Okay? The rock has a larger mass, so it feels a larger force of gravity. Now, before you start writing some things down, hold on a second. We're going to summarize this in the next slide. Okay? So just listen for now. Okay? Meaning that if I take a look here at this bowling ball and this golf ball, and I drew the force of gravity acting on them, they would not experience the same force. Big force for the bowling ball, little force for gravity. But the acceleration of that object doesn't just depend on force. It also depends on what? Acceleration. Maddie, acceleration depends on what?
Net force and mass.
Net force and mass. Okay? So this object is experiencing a much bigger force, but it also has a much bigger mass. So a bigger force should mean what about the acceleration? A bigger force should cause a bigger acceleration, right? Because that's what force and acceleration are related. But what would a bigger mass do? Cause a smaller acceleration, right? So you got one thing that's causing acceleration to go up and another thing that's causing acceleration to go down. Here, this doesn't have very much force, right? But how much mass does it have? Not a whole lot. So these two factors, at least as it relates to acceleration, sort of cancel each other out. Does that make sense? And as a result, we end up with two objects that have the same acceleration. As long as we're talking about what force? Gravity. Because the force of gravity depends on how big the object is. Does that make sense? We okay with that? So, going back to this picture, right? The increased force on the rock should cause more acceleration. But its increased mass cancels out that effect, and we end up with both objects experiencing the same acceleration. Okay, go ahead.
Do we write this down?
That's the space that's next to that picture on the back side. Okay? So you have to summarize this somehow, right? You can write it if you want to, or just kind of summarize it. You know. Okay. But keep in mind, that only applies if we're talking about the force caused by what? Gravity. So if we're talking about gravity causing the force, we will see objects having the same acceleration as each other. On Earth, if we're talking about just the gravity of Earth, what would that acceleration be? Close to 10, right? 10 meters per second squared. On the moon, is it that big? No. Those objects on the moon accelerate the same as each other, but not quite as quickly as they would here on Earth. The important thing being that when objects are under the influence of gravity and gravity only, they will experience the same acceleration. So when objects are under the influence of gravity and gravity only, they will experience the same acceleration as each other. Now, how often do we get to observe objects under the influence of gravity and gravity only? Not a whole lot, right? Because what do we have to deal with here on Earth? Air, right? So let's talk about that, okay? First, air resistance is a force of friction that exists in objects as they move through the air. If it's a resistance force, an air resistance, what direction do you think it's going to act on stuff? It kind of depends, right? But more generally, we can say that it acts which way? Negative or opposite or something, right? Opposite of the way that it's moving. So if I drop an object, which way would air resistance act on it? Upward. If I throw an object into the air, which way does air resistance act on it? Downward while it's traveling up, but when it starts coming back down, then air resistance switches and goes back up. Okay? But air resistance comes from something basically running into air particles as it's traveling through the air. Meaning, if I go faster what happens to air resistance? If it's running into more air particles, the faster I run, how many air particles do I run into? More. So as things go faster, the force of air resistance increases. The faster you go, the more air resistance you encounter. Okay, think about it as you ride your bike. Right, if you start off real slow, you don't feel a whole lot of air resistance, but the faster you go, you feel more of that air, pushing against you, trying to slow you down.
Sucks when you're windy.
Yeah, it does.
It's like when you're running in a soccer game and the wind is just like so strong and you're trying to go this way and it's so
I mean,
hard.
that's even
That's when
increasing.
your legs start to feel like cement.
That's even increasing your air resistance even more, right? Because now,
Playing
Matt-
soccer is
Maddie,
the biggest
when it's windy out, it's not just you running into the air, but the air is also running into you, right? So when you're running into the air, into the wind, you experience even more air resistance because there's more air particles running into you.
And if it's in an open area too. 'Cause
That
it
too.
smells
Like
like
there's windy games where like the goalie punted the ball and the ball just like stalled in the air.
Yeah, Sunday wasn't so hot. It was pretty windy.
Sunday was terrible.
Sunday
Kind of
was
like-
worse.
All right, so let's take a look at this. Let's take a look at this skydiver here, right? You have 4 pictures of this skydiver. We're gonna do like kind of steps as we go along here, okay? So let's say this skydiver is on top of like a really tall building or something like that. She's not jumping out of a plane. She's just like stepping off of something, okay? Base jumping, if you will. Yes. Okay. So, we all know, hopefully you know, that if you step off of a tall building, what's going to start happening to you? You're going to fall, right? And as you fall, hopefully you know that. And if not, now you do. So be careful, okay?
I jumped off a rock.
Because you have a force acting on you, right? That force from what? Gravity. Once you step off the ledge, or whatever it is that you were standing on, is there a normal force acting on you anymore? No. Is gravity balanced out by anything? No. So if there's a force downward on you, but no force upwards, what's going to start happening to you? You're going to start falling. And as you start falling, you're going to increase in speed, right? There you go. There you go. You're faster now. Look at it. Whoa. But even though there is no floor underneath you, the faster you go, what's going to start happening? Now you're going to start encountering air resistance, okay? So, second picture. Now there's this force. Maddie, go ahead.
Is that how they do the skydiving in the indoor places?
Kind of, yeah. Hold on one second to that thought.
My cousin went and I got to watch and it was so fun.
Hold on to that thought just for a second, okay? So, now that you're going faster, you start encountering air resistance. And because it's a resistance force, right, it goes which way? Opposite of the way that you're going. Now, in this picture, is the skydiver accelerating? Yes. Are the forces balanced? No. There is a much greater force downward than there is upward. Therefore, acceleration will continue. Physically, what are we going to see happening to this skydiver? She's going to keep what? No. She's not going to slow down yet.
It's gonna be like shaky.
She's going to speed up. Because which way is she going? Downward. And which way is the force bigger?
Downward.
So if you're moving in a direction and somebody's pulling you in that same direction, what are you going to do? You're going to go faster, right? But as you go faster, right, what starts happening to that air resistance force? Third picture.
But I don't understand why it goes faster initially. I don't understand that.
Because, Becca, when you first step off the edge of that, whatever it is you're standing on, what is your initial velocity? 0. So if you're at rest and you have a force acting on you, what are you going to do?
Speed up.
Speed up, right? If you're already moving and you have a force acting on you in the same direction that you're moving, right? Becca, that's just the that's the lab we did out in the hallway, right? Oh, never mind. So. All right. This picture. Is she still accelerating? Yes. Is she accelerating as much as she was before? No. But she's still doing what? Speeding up. Does she have a big speed? Yes. Because the whole time, what has she been doing? Speeding up. Faster, 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 faster. She has a large speed, but not a very large what? Acceleration. She will continue to go faster though, like this, right? And then eventually, nope, not yet. Then eventually she goes fast enough that what do we see about green and red? Fourth picture. Yes. So, no. Alright? So, so, good. Alright, so,
Oh, because it's balanced out.
so, Maddie,
Yes.
these forces are balanced. So what would we say about this skydiver right now?
She's experiencing equilibrium.
She is in equilibrium, right? Becca, what does that mean about her acceleration?
It's 0.
It is 0. Does that mean she is stopped? No. That means she is going to do what? Stop accelerating. Whatever she was doing at the moment those forces balance, she will continue doing. Katie, totally forgot your name for a second. Katie, what do we call that idea?
Wait for,
That she's getting
Newton's first law.
Newton's first law, inertia, right? Okay. In this case, she's going to keep moving. How? With a constant velocity. We call this idea terminal velocity. Okay? Terminal velocity occurs when the force of gravity from the Earth is balanced out by air resistance, and the net force is equal to 0. Air resistance. When the net force is 0, that means that an object is going to fall with a constant velocity, which means that object is in equilibrium and it will not speed up anymore. We call this idea terminal velocity.
How would we, is there more than, does it have to be like going up and down, or can it be sideways too?
It could be sideways. Becca, I mean, you could talk about like a car on cruise control. Do you know what cruise control is on a car? Okay. So there is a force from the engine that is pushing it forward. But as it pushes it forward, it goes faster and it runs into air resistance. So on cruise control, when that car is going with a constant speed, the force of the engine pushing it forward is balanced out by the resistance force from air resistance that it's running into. You could say that's kind of like terminal velocity, right? It technically wouldn't be the force of gravity that's pulling it forward, but it's kind of like terminal velocity, okay? Maddie, you said before, right? You can recreate this without having to fall through the air. If you do what?
You have enough air resistance.
If you have enough air resistance, like let's say the floor is a big fan, right? Which is what you do in like those indoor skydiving places, right?
It could be 16.
Yeah. Next year. But in those indoor skydiving places, right, the picture is no different than this picture on the right. It's just that instead of this upwards force coming from air resistance as you fall, it's coming from a fan pushing a bunch of air up on top of you or up into you. Right? Does that make sense? that has concept development practice page. We did 4-1, or a good portion of it, and we did 5-2, but we didn't do 5-1 in the middle, especially the back of 5-1. The back of concept development practice page 5-1 tells you about a skydiver. This skydiver's name is Bronco. Alright? So,
That's a tough name.
that is totally a tough name. So,
It's my name.
if we take a look, it tells you, well, that'll be important in a second, Becca. Hold on a second. Okay. So if we look at Bronco, I'm going to take Bronco, and I'm going to put him here next to the story about himself. So here's Bronco, alright? So it tells you that Bronco skydives out of a helicopter, meaning that he's going to fall straight down, okay? He's not jumping out of a plane or anything like that, okay? And you can see along the right-hand side of the page, it shows Bronco at different parts of his flight. I'm actually going to pull up letter B first before we do letter A. So here's Bronco, cut Bronco here, paste it here, and let's go here. Okay, so there's Bronco at part B. And it wants us to find out what is Bronco's acceleration. So we have already discussed, right, that, I'm going to do this real quick. I'm going to get rid of this part right here. Okay? Because I want to make sure you understand where that comes from. This part, right here. Does that look familiar? I hope so. It's Newton's second law, right? And we said that the acceleration is dependent on two things, net force and mass. If we look at this picture here, in part B for Bronco, how many forces are there acting on him? Two. The first one is labeled W. Why do you think it's labeled W? For weight, right? But I'm going to take that away and I'm going to call that F of G, okay? Because that's the force of gravity. And we learned yesterday that we can figure out the force of gravity acting on something, right? How do we do that? How do we calculate the force of gravity acting on something?
Mass times gravity.
M times G, right? Where M stands for what? Mass. It tells us in the story that Bronco's mass is 100 kilograms. So we know his mass. And what did we say that G represented? The acceleration of gravity. Here on Earth, what is that value? Pretty close to 10, right? So 100 times 10 is equal to what? 1,000 newtons. Okay? Now, what do you think this R is probably going to represent? Resistance. Why don't we call that F sub R, right, for force of resistance? Okay. Now, the one thing that we have to do here that your paper does for us is we got to assign directions. Your paper decides it's going to call downward the positive direction, because that's the way that Bronco's falling. And that means that if downward is the positive direction, what else? That means upward is the negative direction. Okay? So, if we take this value, or this equation for Newton's second law, we can change it to look like this. A equals, what did we say that F net meant, or sigma F? The sum, right? So technically this would be F of G plus F of R all over M. Right? So for this section right here, we can start plugging in things that we know. For example, do we know what F of G is? It's what? 1,000, but which way is it going? So positive 1,000, right? Plus, what's the air resistance force in this picture? Negative 400. All divided by Bronco's mass, which we know is just 100, because it doesn't have, mass is a scalar, it doesn't have direction, right? So, you plug that into your calculator, or you just do it in your head, and you find out that Bronco's acceleration at that point is what? Except it's really positive 6, right? If he has positive acceleration, what's physically happening to Bronco in this case? He's speeding up as he falls down, okay? And that will continue until he reaches point C. Here's point C in the picture. Do we have to do any calculations in this one? What's Bronco's acceleration at this point? 0, because the forces are balanced. What would we say about Bronco at this point? Equilibrium, or we could call that terminal velocity. Okay? But if we take a look one picture after that, what does Bronco do? Pulls a parachute, right? What does a parachute do to the amount of resistance that you have? It increases it, right? So now we go A is equal to the force of gravity, which we know is positive 1,000, plus the force of resistance, which now is what? Negative 1,200. Divide all that by Bronco's mass, and we see that his acceleration at this point is what? Negative 2. What is Bronco doing at this point in time? He's starting to slow down. As he slows down, what happens to his resistance force? If he slows down, the resistance that he experiences actually
Larger than his weight.
well, at this point, yes. But if he continues to slow down, how much air does he run into? Less. Because he's not going as fast. Which means eventually he will end up like this. What's his acceleration here? 0. He's back in equilibrium. He's also back where? Terminal velocity. Is it the same terminal velocity as before? No, but it's still terminal velocity. Okay? So here's what I want you to do for tonight. These questions over here on the left-hand side, finish them up for me based on those pictures. Also, I want to continue to finish all the accelerations. Okay? And then on the front of that page, there's a guy in a box. And that will serve as our discussion point for tomorrow. I will post the answers online. Okay? Good job today, everybody. I will see you tomorrow.